In this video, we will represent linear relationships using verbal descriptions, tables, graphs, and equations that simplify to the form y equals mx plus b. So for these notes, we're going to be taking notes in our Cornell Notes format. Our driving question or our essential question is, how can you express a linear relationship between two quantities in different ways? Again, our essential question for this set of notes is, how can you express a linear relationship between two quantities in different ways? So first off, a linear relationship, the definition for that is a relationship between two quantities, an x and a y, I made a little typo there, that have a constant rate of change and a straight line graph. So in order for the relationship to be linear, it must satisfy both of these requirements. It has to have a constant rate of change and a straight line graph. It's almost impossible to have a straight line graph without a constant rate of change, which we'll talk a little bit about later, but it has to have both of these. Determining whether a relationship is linear using a table. So before we started talking about linear relationships, we learned how to find the rate of change for a relationship, talking about the rate of change between our y and our x. So our rate of change we usually express as the change in y, and we use a little triangle, it's the Greek symbol delta, to express change over the change in x. So whenever we have a table, we can determine whether the relationship in the table is linear just by finding the rate of change. And if there's a constant rate of change, then this means that the relationship in the table is linear. So if we're looking at this first table here, then we're going to look at our rate of change for the y. So y, if we look from one column to the next, it's increasing by 2. Here, again, it's increasing by 2. And in the last one, it is also increasing by 2. So we can say that our change in y here is 2. And then if we look at the x row in our table, we're going to also find the change here. So from one column to the next, plus 2. Again, plus 2. And lastly, again, it's increasing by 2. So our y was increasing by 2 every single time, which is constant. Our x was also increasing by 2 every time, which is constant. We have a rate of change of 2 over 2, or if we simplify that, simply put, is 1. So our rate of change here was 1. It was a constant rate of change. So we would say that this table right here, the relationship is linear. Now let's look at this second table. So again, we're looking at the rate of change for this second table here, and we're looking at the change in y compared to the change in x. So if we look at the change in y here, it increases by 4. Here, our y value is increasing by 8. And then here, it's increasing by 16. Okay? Now, we can already begin to tell that there's not a constant rate of change here. But we're going to look at the x row to compare it. So here, it increases by 1. Here, it increases by 1 again. Here, it increases by 1. So if we took each one of these columns and we did y over x, right, going back to the constant of proportionality, if we did y over x for this one here, this would be 6 over 1 here, right? We're looking at these two values, 6 over 1, which y over x, that's 6 over 1, would simplify to 6. If we look at these two values here, our 2 and our 14, if we were to write them as y over x, this 14 over 2 would simplify to 7. So we can see that the relationship in this table here is not linear. It does not represent a linear relationship. Determining whether a relationship is linear using a graph. Looking at graphs are pretty straightforward determining linear relationships. We said that the graph has to have a constant rate of change and a straight line. So if we look at both of these graphs, they have perfectly straight lines. It's easy to see here that they represent linear relationships. Now, if you're ever putting points on a graph, if you're ever plotting out a line and it doesn't make a perfect line, then it is not a linear relationship. Linear equation, slope-intercept form. So whenever we represent a linear relationship in an equation, such as y equals 60x or y equals 2x plus 4, we call those linear equations. Linear equations are written in slope-intercept form, y equals mx plus b. They're written in slope-intercept form, y equals mx plus b, where the m represents the rate of change, right? So if we're talking about our m in this equation, it's our coefficient 2, and b represents the y-intercept, right? This is the point on our graph where our line crosses the y-axis. So if we're looking at this equation, y equals 2x plus 4, the 2, the coefficient here, represents our m, our rate of change, and then the 4 here represents our y-intercept, the point where the line crosses the y-axis. Now I'm going to draw a quick picture here of what a coordinate plane would look like, right? So this is our x and our y-axis. Now if we had a line here, again, my line is terrible. I apologize. I was trying to create a straight line. When we talk about the y-intercept, it's the point where our line crosses the y-axis. So here, this spot right here, this point right here on our graph would be our y-axis, our y-intercept. So in this case, we said our y-intercept was 4, which if we wrote that out as an ordered pair would be 0, 4, right? This would be the point where our line intercepts the y-axis. And again, forgive me for this crude drawing, but we'll look at some other examples. So y equals 4x plus 3. We said that the m represents our rate of change here. So we see m equals 4, and then the b, our y-intercept, the point where our line crosses the y-axis, is 3. Here's a little graphic organizer for you to copy down into your notes on examples and definitions. You might see these in word problems, so this is a little handy organizer for you to refer back to. Y equals mx plus b. That m and the x, whenever we have two letters next to each other, or whether we have a letter and a number next to each other, that always represents multiplication. So in this case, this is saying m times x plus b, right? M being our rate of change or our slope. We won't really hear slope a lot in 7th grade, but you will hear it in 8th grade. So the m represents our rate of change or slope. You'll see this in word problems as miles per hour, dollars per pounds, dollars per minutes, or dollars per hours. Our x is usually our input. So for instance, this is our independent variable. We talk a lot about our independent variable in class. This could be time. Time is usually independent. This could be mass, volume, weight, distance. It could be a number of things. And then B, our y-intercept. This is usually a starting point. So if you notice when you look at a graph, your y-intercept, usually a line will often start at the B, right? So again, if I have a graph here, my line may start from this point, the y-intercept. And this may be a starting point, a minimum fee, a one-time fee, registration fee. We'll see a lot of different A lot of different examples, but it's usually a starting point. And then last but not least, our y is our output. So when we put in our input x, whether that's time or weight or distance, whatever it is, whenever we put this in and we multiply it by our m and add it to our b, it's going to give us our y. So let's say we had the equation 4x plus 2 equals y, right? So y equals 4x plus 2. Now, if we were to say our x value was 3, right? Let's say maybe 3 minutes. So if our x value was 3, we would plug in 3 for the x, which means we're going to be multiplying 4 times 3 plus 2. Our x here was our input, which means whatever we put in here and we multiply by the 4 and add it to 2, it's going to give us our output, our y value. So if we simplify this, 4 times 3 is 12. 12 plus 2 is 14. So here y would be equal to 14.